na lossy. Okay, so electromagnetic induction. First of all, we can have current creating a what? A magnetic field. And then the interaction causes motion. And you could have a magnet and a coil, or a conductor for that matter, that moves relative to each other. So the motion causes electricity. Okay, so we have two situations. One, we have a current flowing in a conductor that is placed in a magnetic field, and that causes motion. The other one is where you take a conductor, you move it in a magnetic field, and it creates electricity. Okay, so let's take our conductor. There are some ways of representing conductors that is conducting current. What does the dot mean? The current. Which current is coming out towards you? Conventional current. So conventional current flows out of the page. Okay, I see. The juices are moving. And conventional current are flowing away from you. So current towards you, current away from you. What did we have here? What do we have when we have a conductor taking current in this direction? Which rule did we use? The right hand grip rule, where your thumb points in the direction of the current and your fingers will curl in the direction of the magnetic field. So the magnetic field around this conductor will be anti-clockwise. Okay, I'm not going to go into it further because we worked from here to a loop to a coil last year. And here our right hand rule's fingers will curl clockwise. Okay, so the magnetic field is clockwise. Here, this year, we're going to apply this on motors. Okay, so let us build a little motor here. We draw a permanent magnet. There is a permanent magnet north to south is the direction of the magnetic field. I want you to look first before you copy. Okay. So the magnetic field of the permanent magnet is always from north to south. Alright? Let's indicate that. North to south is the magnetic field of the permanent magnets, always. Okay? Now we can see that there's interaction between those two magnetic fields and this one. We can see that in some places they are perpendicular. There, the conductor's magnetic field will point down. and the magnetic field of the permanent magnet is going across. Can you see that? Here, the magnetic field of the conductor is in that direction. There it's in that direction. There it's in that direction. And there it's in that direction. There, the current magnetic field is in that direction. There it's in that direction. Here it's in this direction. There it is in that direction. Okay? Where the two, the red and the blue magnetic fields, are opposing each other. The red one is to the right and this blue one is to the left. What will happen there? They repel each other there. They create a void of magnetic fields. Let me draw the red one to show you what will happen. Here, the magnetic field will go up like that. And there, the magnetic field of the permanent magnet is in the same direction as the blue one. Below, it's in the same direction as the blue one, but here it's opposing, so it will be pushed away. What's this thing going to do? This part here is going to move upwards. This part here is going to move downwards. Now, when magnetic fields are 90 degrees with respect to each other like this, they have no effect on each other. But when they are opposing or when they're in the same direction, they do have an effect. Here you'll have a strong magnetic field created at the bottom here and a very weak one. So what will happen? This thing will be pushed up. It's called the motor effect. There you'll have a very strong magnetic field pushing down. There you'll have hardly any magnetic field. So this one will move down. And we have a rule. We can't guess or memorize this. It's too much. So we have Fleming's left-hand motor rule to help us to get the direction of the motion of the loop or the conductor or the coil. Are you with me? So you take your left hand, you put your index finger, your index finger, your middle finger and your thumb at 90 degrees. Okay? The middle finger is for current. The index finger is for the magnet's magnetic field. And your thumb will indicate the thrust or the force on the conductor. So, middle finger, current coming out towards me. Index finger, magnetic field going to the right. And this part of the conductor will move up. So electricity creates motion. There, the current is flowing away from you. Middle finger away from you. Index finger still from left to right. This part of the conductor will move down. So this thing is going to turn clockwise. Are you with me? Good. Yeah, so here we use Fleming's left hand motor rule to determine the force on conductor. So this is called the motor effect. Okay, this looks very messy now, so I'm going to take some of these things away. I'm going to take that one away. And I'm going to take this one away. And I'm going to take that one away. Can you remember what the symbol for magnetic field is?
Oh, ma'am, although we didn't do like calculations last year.
No, we didn't, but
it's
a B field. Magnetic field B. It's not. It's just making my writing easier. So here a current is creating a magnetic field, and the interaction between the magnetic fields causes motion. And the direction of the motion will be determined by Fleming's left-hand motor rule. Are you ready? So, not yet? Okay. So let's look at what happens when you move a conductor in a magnetic field. I'll start off with 1. So, you know this represents a loop. Are you alright with that? Okay. Let's move one conductor in the magnetic field. Wait with your copying. I'll give you a chance to copy. In which direction do you want to move the conductor? It's a conductor. I'm drawing an open circle because there's no current flowing through it. But I want to move it in a magnetic field. It's called electromagnetic induction. You are inducing a current here, mutual induction. If you've got a magnetic field, so this one is your magnetic field. It is from north to south. And I want to take this conductor and I want to move it in the magnetic field. Where will I move it to? Will it help if I take this conductor and I move it like this, going with the lines of the permanent magnetic field? Okay. When you do that, you do not change the magnetic flux that is linked to the conductor. I'm using last year's terminology now. So if you do that, there's no change in magnetic flux. So there will be no induced current. With the moment you move it up or down, there will be an induced current. Okay? So if we move it up, what's the direction of the induced current? If you move it down, what's the direction of the induced current? So there is a way to find it. We can, first of all, let's say we move the conductor up. So the green arrow is indicating the motion, the force that is exerted on the conductor. Here, instead of using Fleming's left-hand motor rule, we're going to use Fleming's right-hand dynamo rule. Okay? So your right hand's fingers are held at 90 degrees. The index finger will point in the direction of the permanent magnetic field. Your thumb points in the direction of the motion, and then your middle finger will point automatically in the direction of the induced current. What? I am moving this coil in the magnetic field. I am moving it. So you are using mechanical energy to move the conductor. Okay? So we used Fleming's left-hand motor rule when we had electricity in the coil. to see in which direction is it going to move. Now we're using Fleming's right hand dynamo rule. So the index finger must point north-south. The thumb must point in the direction of motion. In which direction will the current flow through the conductor? Away from you. If you move the conductor down, then the current is going to flow towards you. This becomes funny when a science teacher is invigilating, because you're going to sit there. You need to know which hand to use where. Okay, so if this is the case, then the current is going to flow away from you. So if I take this part of the conductor, I'm going to change it into a loop now, and I move it up, then the current is going to flow in that conductor away from you. Yes?
Ma'am, is it a left hand or the right hand?
This one is Fleming's right hand rule.
Oh, the one on the textbook is talking about what you see right now.
Yes.
Okay.
Is it?
Yes, ma'am.
Yes, ma'am.
Okay. Fleming's right hand dynamo rule. It determines the direction of current induced. Okay, so if we make it a loop, then automatically this loop is going to, if the left hand part of the loop is going to turn up, the right hand part of the loop is going to turn down. So in which direction is the induced current on the right hand side of the loop? It's going to be towards you. Now we are going to look at the construction of your, yes. Okay, let's see how we can hold it. So this one must point that way. And the motion is down. So this is very awkward. What I would do is I'll turn the book upside down so that it will be better for me. I'll turn this whole book upside down so that the south is that side and the north is that side, so that my finger will be there. Then this arrow will be pointing up, but this finger will come out, but the whole thing will be turned upside down, rather than trying to do this. No, it needs to go that way. Okay. But in any case, when you work with a motor or a generator, if the current flows away on the left hand side, it's going to come towards you on the right hand side. Okay. I want to go to my model and I want to show you. No, wait a moment. Let me just go. Give you a chance to copy here, and just want to say, just for the sake, I don't know whether this is called the dynamo effect in your textbook. Yes, but the dynamo effect applies to the generator, the motor effect applies to the motor. So I'm going to demonstrate the dynamo effect first. Okay, are you ready for my demonstration? Ready for my demonstration? Okay, so I'm going to go to the visualizer now. I might have to just adjust it so that you can see what's going on. Okay, So you can see the North Pole and the South Pole, and you can see there is a coil in the magnetic field of the magnets. Okay? So I'm holding it. This yellow part is labeled A. The orange part is labeled B. Okay? So it's a generator. So I'm using my hand to turn the coil. In which direction will the current move here? So it is a generator, so I have to use my right hand dynamo rule. So if the motion is up and the magnetic field is from north to south, then the current in the yellow part is going to go in that direction. Okay, you got it. Okay, so this is going to be called the induced current. It gets to the induced current will flow in that direction. Then we get to the point where the loop is moving with the magnetic field. Will there be any current in there now? When it moves through that position. We discussed it. If the conductor moves parallel to the magnetic field, no current will flow. Alright? When I move it to this direction, in which direction will the current flow? There. As I keep rotating it. This part is now moving down. Okay? While the orange part is moving up. In which direction is the current in the yellow part now going to be when it is flipped over to this side? It's going to move. Current is going to flow in that direction. Can you see that when the yellow was in this position, moving up in this position, the current was flowing in that direction through the yellow? Okay, you don't have a fight about that. The current stops flowing when we get to the vertical position. You don't have a fight about that. Okay, and the moment you carry on turning it, the current swaps direction there. Can you see that? Then the current will go in that direction through the orange, and when it gets to the vertical position again, there's no current flowing through it. And then when it moves over to the other side, the current is flowing in that direction. Okay. So what happens to the current in the external circuit is the big question. Because you can see in this circuit, it is in the loop, it's flipping. Every time it's flipping. Alright. What's happening to the current in the external circuit? That would depend on this part here. This part is called slip rings. Okay, let me take it out so that I can show you. Okay, can you see that B is connected to this part? Orange to orange. A is connected to this part. Alright, so these are called slip rings. And there are something called a brush that runs against the slip ring. That is connected to the B part of the loop. And there is something called a brush running against the yellow part, slip ring. If I go to this one, can you see that B is connected to orange, A is connected to yellow? Can you see that this thing is called a split ring? There's a split in it. So it's called a split ring commutator. So your brushes will run touching this thing all the time. And when the brushes touches both the slips of the ring, then no current will flow through the coil. We need to discuss that. Yes.
So will the direction change in that one?
Let's see. We're still on the generator. If it's turned in that direction, what will the direction of current be? Like that. The moment it goes through the through the vertical point, there's no current. The moment you carry on turning it over to the other side, the current is going to flow there. Okay. Now we need to know, so the current will do the same thing. Now we need to know what's going to happen here. Okay. So we're going to connect our generator to an external circuit. I need to draw my external circuit in there. I'm talking about that thing. Like a light bulb.
What you are, like the source.
This is the generator. So I need to connect the generator to a circuit. Let's connect the generator to a circuit. Okay. Come now. Okay, so I'm going to connect. This is called a brush. And it's touching the slip ring there. And this is called a brush, touching the slip ring there. And I just want to get to, let's give it a light bulb there. So this is my external circuit that is connected to my generator. Okay, I'm going to try and so if we turn the coil clockwise, what's going to happen? This is the turn. Okay, what's going to happen to the current here in A? It's going to flow in that direction. What's going to happen to the current in B? It's going to flow in this direction. So here the current comes, it goes down here, it flows, goes into the slip ring, and the current is in that direction. Am I right? While this thing is moving up like that, the current is in this direction and it comes in here. Sorry, my pen is in the way here. So it flows in this direction. That is the motion of the current in this coil. Okay. What happens when we reach the vertical position? There's no current. So the whole current is dead. In the vertical position, there is no current. No current in this coil. Nothing. Okay? Remember that orange is connected to orange and yellow is connected to yellow. Oops, wrong one. Okay. Back to. Now, yellow. In which direction is current flowing now? It's coming down the yellow part, right? And remember it's going to the yellow part out there. Can you see what happened to the direction of the current now in the external circuit? it's changing direction. It's going in the opposite direction. Can you see that, please? Okay. So what is this generator called? This generator is called an AC generator because the current in the external circuit is changing direction. Let's go again. Okay? So remember, the current comes out through A and it flows through our external circuit into B. Now, as we turn it that way, just want to, when we get to the vertical position, there is no current. No current in the vertical position. Just try and do this more carefully. No current when the coil is in the vertical position. Now A is where it was when we started. What is the direction of the current in A? It is in this direction. So it is coming in through the slip ring. So now the current is coming like this. And in B's part, the current is coming out. So there, the current is flowing in the clockwise direction in the external circuit. When we get to the vertical position again, there is no current. Are you with me?
Yes, ma'am.
So in the vertical position, there will always be no current. But now A and B parts have changed position. They've flipped over. So what is the direction of the current in B now? It is in that direction, and in A it is in that direction. So it comes out A and in to B. So what happened to the direction in your external circuit, the direction of current? It has changed. Now it flows anti-clockwise through that circuit. So what type of current is this? Alternating current, because it changes direction through the external circuit as the generator is rotated. As it turns, every 180 degrees, the current in your circuit will change direction. That is when we have slip rings. So you need to link slip rings to alternating current generator. Slip rings, AC generator. And the function of the slip rings, it's to allow contact between the external circuit and the generator. If these were not brushes touching the slip rings, then your wires would all be entangled as this thing is turning. Won't be an effective motor, generator. I think I'll do the DC next week. What I do want to say here, so that it is on this, when the coil is in the vertical position, no current, as it turns, it generates an increasing current, because the magnetic field, the magnetic flux change going through the coil is getting bigger. There, all the magnetic field lines of the magnets are running through the coil. What happens to it when it turns to the horizontal position is a bigger current is generated. As it turns further, a smaller current is generated till it's 0 again. Then it flips over and it flows in the opposite direction, getting stronger and weaker, stronger and weaker. That's enough for this. Yes.
Does it affect the brightness of the bulb?
Yes, the